Simplify the square root of 24. Whenever I'm being asked to simplify a square root, I like to go off to the side and make a nice little factor tree. So two numbers that multiply out to 24 are 2 and 12. Can't do much with 12, except that we can rip out a 4 and a 3 and circle U, and 4 becomes U and U. So 24 can be written out in its prime factorization as 2 times 2 times 2 times 3. And write it out in order, please. 2 times 2 times 2 times 3. Once you have it all written out, look for pairs of identical numbers. Circle each pair, pull one out. I'm out, so I can pull out a single 2, and I'm left with 2 times 3, which is 6. So the answer is 2 times the square root of 6, baby. Simplify the cubed root of negative 162. First off, ignore that negative. Let's go over here and make ourselves a nice little factor tree. Now, two numbers that multiply out to 162 are 81 and 2. Circle the 2. 81 is 9 and 9, do nothing. And then each 9 is 3 and 3, so you're also 3 and 3. So we can write out the cube root of negative 162 as 2 times 3 times 3 times 3 times 3. Write it out in order. Now there's a negative here. Let's put that there. Now the cube root of a negative means you can just pull out the negative, okay? Now what we're going to do is we're going to find groups of 3 identical numbers. 2 is alone. Here's a group of 3 3s, pull one out. So 3 is going to come on out along with the negative. You have a single 3 left over, can't do anything about it. So what's left over is the cube root of 2 times 3. So this becomes negative 3 times the cube root of 6. And you're done. Simplify the fourth root of 128 n to the 8th power. All right, well, let's go off to the side and make a factor tree out of 128. 128 can be 2 and 64. Circle the 2. 64 can be 8 and 8. Circle none of those. 8 can be 2 and 4. Circle the 2. 4 can be 2 and 2. Circle the 2s. And this 8 is going to literally be the same exact thing. So, writing this all out, the fourth root of 128 is going to be 2 times 2 times 2 times 2 times 2 times 2 times 2. That is 8 2s. So 2 times 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 2. End of the 8th is 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7, 8. So 8 ends, 8 2s. Since this is a fourth root, look for groups of 4 identical numbers and pull one of each out. So here's a group of 4 2s. Here's another group of 4 2s. Here's a group of 4 n's. Here's another group of 4 n's, and I literally have nothing left over. So you bring out a 2, you bring out another 2, you bring out an n, you bring out another n, and the fourth root rather is gone. 2 times 2 is 4, n times n is n squared, 4n squared is going to be your guy. Simplify the sixth root of 448 x to the 7th, y to the 7th. All right, so let's go over to 448 and let's make a factor tree out of that and see what we can come up with. We can divide by 2 and leaves us with 224, circle the 2. Factor of 2 again, 117, and 2, 117, I think you're done. But here's the thing, I'm not 100% sure, but even if you are done, there's no way 117 is going to turn into 6 specific numbers. So I'm going to leave that like that. I'm assuming you're prime. I could be wrong. That's all right. Now what we do is rewrite out the prime factorization, 2 times 117. Then we write out all the x's times x, 2, 3, 4, 5, 6, 7, and then we write out all the y's, 1, 2, 3, 4, 5, 6, 7. Since we're taking the sixth root, circle all pairs of identical numbers. Not all pairs, all groups of 6 of the same number, which is why I didn't lose any sleep about the whole 117 thing, because there's no way 117 is going to turn into 4 more 2s or anything like that. So what I could do is I could circle a group of 6 x's right there, and I could circle that group of 6 y's right there. And what I'm left with is an x out here, a y out here. That 2 times 2 times 17 I already know is 448. So why don't I turn that back? X, y. So this whole thing becomes x, y times the 6th root of 448 x, y. Nifty-galifty. Simplify negative 3 times the square root of 12 plus 3 times the square root of 3 plus 3 times the square root of 20. Right now, at this very moment, there's nothing you can do. But what we're going to try to do is see if we can simplify each of these square roots and maybe add like roots, kind of like combining like terms. So 12 over here can be split up into 3 and 4 can be split up into 2 and 2. So I can turn 3 times the square root of 12, negative 3 times the square root of 12. I can turn that into 2 times 3. Circle a pair of 2's. Bring it out. That leaves me with negative 3 times 2 times the square root of 3, which is negative 6 times the square root of 3. Fortunately, this guy is already 3 times the square root of 3. So these two will combine. Let's see if anything happens with that 20. Now if I go to 20, make a factor tree out of that, I can do 4 and 5. You can circle a 5. I can do 2 and 2, circle both of those. So 3 root 20 is the same as 3 root 2 times 5. Circle a group of 2's, bring it out. So you have positive 3 times root 2, and what you have, times regular 2, and you have root 5 left over, which is positive 6 root 5. Now, if you look at the 3, these two will combine because they're both root 3's. You stand alone. So if I have negative 6 root 3's plus 3 root 3's, that gives me negative 3 root 3's, just like as if you were combining like terms. Okay, and we're going to add 6 root 5. And that's how you do it. Simplify negative cube root of 320 minus 4 times the cube root of 5 plus 2 times the cube root of 135 plus 2 times the cube root of 16. What we have to do is simplify each of these cube roots and see if any of them combine like they're like terms. So let's go to 320. Let's make a factor tree out of that. So let's do 32 and 10. Okay, let's do 8 and 4. Let's do 4 and 2, so we can circle a 2. Let's do 2 and 2. 4 is also 2 and 2. And 10 is 5 and 2. So doing this one at a time, negative cube root of 320 is going to be 2, 2, 2, 2, 2, 2. 1, 2, 3, 4, 5, 6. So 2 times 2 times 2 times 2 times 2 times 2, and then times 5. With a cube root, you circle identical groups of 2 and bring each one out. So bring out 1, 2, and bring out another 2. So that's negative 2 times the cube root of 5, which is negative 4 times the cube root of 5. That's one thing. Let's do it again. Now, fortunately with you can't do anything. So why don't I just drop that down and make that minus 4 cube root of 5. Now those don't cancel out because you're negative and you're negative, so they don't cancel each other out. Don't get all antsy. With 135, let's see what we can do with that. So let's make a factor tree out of 135. Let me see. I can do 5 and 2, 27. And 27 is 3 and 9. And 9 is 3 and 3. So this becomes 2 cube root of 3335. Circle an identical pair of 3's and bring it out. That's already there with the 2. So 2 times 3 is going to be 6. So let me write that out. 2 times 3, cube root of whatever's left over is 5. That's going to be positive 6 cube root of 5. Last but not least, we have 16. 16, let's use a different color, is going to be 4 and 4, which is going to be 2 and 2, and 2 and 2, like that. So 2 times the cube root of 2 times 2 times 2 times 2, circle a group of identical 2's, 3 of them, bring out 1 of them. So you become 2 times 2 cube root of 2, which is positive 4 cube root of 2. Now, let's see what can combine. All right, u and u and u all have a cube root of 5 attached. So negative 4 minus 4 is negative 8. Negative 8 plus 6 is negative 2. Negative 2 cube root of 5. What about this guy? Well, there's nothing like him, so he stands alone. And you're 4 cube root of 2. Yeah, kind of intense, but lots of fun. Simplify the cube root of 3 times the cube root of negative 20. Whenever you multiply cube roots, square roots, fourth roots, or whatever, you're allowed to multiply the insides. So this becomes the cube root of 3 times negative 20, which is negative 60. Now what we're going to do is we're going to go over here and we're going to turn 60 into a factor tree and see what we can rip apart. So 60 is 6 and 10, 6 is 3 and 2, and 10 is 2 and 5. Circle, 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 circle. Now, what I know is with a cube root, I'm supposed to circle groups of identical 3's and pull them out. But here, I don't have a group of 3's to pull out. So there's nothing I can do about that 60. The only thing I can do is if you have a cube root of a negative number, bring out the negative, like that. And in this case, you're going to leave the number. So after all of that, really all we do is multiply the numbers and bring out the negative, and that's the end of that one. Not that bad. Simplify 4 times the square root of 15 times parentheses negative 3 root 6 plus 5. We've got ourselves distributive property. So if we're going to multiply 4 root 15 times negative 3 root 16, multiply the numbers on the outside of the roots individually. Then take the square roots, make one big square root, and multiply the numbers on the inside. The square root of 15 times 6, the square root of 15 times the square root of 6 is going to be the square root of 90, like that. And then we do it again. 20, because 4 times 5 is 20, and then root 15 is kind of just lingering right here, so root 15. Now, 90. Let's see if we can rip that apart. We get 9 and 10, can't do anything there. We get 3 and 3 and 5 and 2. Okay? So negative 12 times the square root of 90 can be written as negative 12 times 2 times 3 times 3 times 5. Now with square roots, you pull out identical pairs of numbers like this. And so we rip out a negative 12 that's already there. We rip out a 3, and then we leave the square root of 2 times 5. Now this square root of 15, if I were to make a quick factor tree, it's going to be 3 and 5. And you should automatically know, like, okay, well, I can't simplify that then. There's nothing I can do with the square root of 15. So we could just drop that down and keep it 20 root 15. And so negative 12 times 3 is negative 36. 2 times 5 is 10, plus 20 square root of 15. These guys can't combine, so we're done. Simplify 2 plus root 5 in a parentheses times parentheses negative 2 plus root 5k. All right, so what we're going to do here is we're going to FOIL this out. So let's use all of our colors. 2 times negative 2 is negative 4, no big deal. NBD, as the kids say. 2 times root 5k is going to be 2 root 5k. Root 5 times negative 2 is negative 2 root 5. So far, nothing crazy has happened. And root 5 times root 5k means I multiply inside the square root. So 5 times 5 is 25k. Now I know that this guy over here is going to be the same as 5 times 5k. And you could circle that 5 and bring out one of them, which leaves us with 5 root k, like so. So seeing what we have left over, I could drop down to -4, nothing combines with it. I have 2 root 5k, there's no root 5k's floating around, so I'm done with that. Minus 2 root 5, there's no root 5's floating around, so I'm done with that. And then 5 root k, there's no root k's, so I'm done with that. So after all of that, nothing combines. It's just we simplified the one, multiplied the rest, easy peasy lemon squeezy. Simplify the square root of 4 over the square root of 36. All right, well, the square root of 4 is 2, and the square root of 36 is 6, which becomes 1/3. Thanks for watching, like and subscribe. Simplify 4 root 2 over 3 root 5. Now, if you're looking at this and saying, oh, there's nothing I can do, yeah, you're kind of correct. But here's the thing. There's a little rule in math that says you're not allowed to have square roots in the denominator. So if all you're doing in the denominator is multiplying and you have a square root, what you do is you multiply the top and the bottom by that square root. This is called rationalizing a denominator. All right, so what's going to happen up here is you have 4 root 2 times 5, which is root 10. On the bottom, you have 3 root 25. Why did we do that? Well, if you're not allowed to have a square root on the bottom, root 25 becomes 5. So we have 4 over 3 times 5, square root of 10 is still upstairs, and that becomes 4 square root of 10 over 15. Can't do anything there. You can't simplify the 10 and the 15. One's inside a square root, the other one's not. So we're done. Simplify -4 plus root 3 over -1 minus 2 root 5. All right, so what's the issue here you're looking at? Like, what do I simplify? What do I cross out? You're not crossing anything out. The issue is there's a square root on the bottom, okay? There's a square root in the denominator, and you're not allowed to have that. Now, in a previous problem, all I had was something that looked like this, right? All I had was a number times the square root of 5, and what I did is I multiplied the top and the bottom times the square root of 5, and that made that square root of 5 disappear, right? Well, I don't have that. I'm adding or subtracting on the bottom. I'm adding or subtracting in the denominator. So the way that we fix this is whenever you have a square root in the way and you're adding or subtracting in the denominator, you multiply the top and the bottom by its conjugate. That's the same exact thing, but flip the sign in the middle. Okay, so -1 plus 2 root 5. Okay, now I'm going to go the extra mile and show us exactly what that looks like. This is a FOIL problem, right? And this is a FOIL problem. All right, so up here, -4 times -1 is +4. -4 times 2 root 5 is -8 root 5. Root 3 times -1 is -root 3. And then 2 root 15. Okay, up here, nothing simplifies, you can't do anything, the numerator is okay. But wait. Down here, I have -1 times -1, which is 1. I have -1 times a positive 2 root 5, which is -2 root 5. I have -2 root 5 times -1, which is positive 2 root 5. And I have -2 root 5 times positive 2 root 5, which is going to be -2 times 2 is 4. And then root 5 times root 5 is root 25. Now, the reason why we multiplied by a conjugate is we created a difference of squares scenario. And always, the middles will cancel out. And so you're saying, okay, well, I see we just lost 2 of those square roots, but what about u? Well, u, the square root of 25, is just 5. So we get on the bottom 1 minus 4 times 5. Okay? On the top, we still have 4 minus 8 root 5 minus root 3 plus 2 root 15, and nothing happens there. But if we do a little bit of quick math, 4 times 5 is 20, and 1 minus 20 is -19. So let's throw the negative out here and put the negative regular 19 on the bottom. Let's write out 4 minus 8 root 5 minus root 3 plus 2 root 15. Not the prettiest, but definitely not the worst. I don't know what I meant by that. It's fine. Write the expression in radical form. Well, there's a little rule that says if you have b to the m over n, right, your base to the exponent that is a fraction power, you can rewrite that as put the b inside the square root, and it's going to be the nth root of that. So the denominator tells you the type of root it is, and the m lives with the b. Or, if you wanted to, you can keep this as the nth root of b, and then write the m on the outside. Either way, it's fine. So with this case, you would be my b, you would be my m, and you would be my n. So I could write this one of two ways. I can write this out as the cubed root of 7 to the 4th power, or I can write this out as the cubed root of 7, all of it to the 4th power. Either way, it's the same exact thing. Write the expression in radical form. All right, well, what I want to do is I want to get this to the point where it looks like b to the m over n. Because once I can write it out like that, I can rewrite this out as the nth root of b to the m power, right? So what I have right now is I have a negative exponent. Let's deal with that first. Negative exponent means you put it to the other side of the fraction bar. And you might be looking at this guy and saying, oh, there is no fraction bar. Sure there is. Right there. It's invisible 1. So if I move it to the other side of the fraction bar, it's now 5x on the bottom to the positive 1/2. Now, what I could do is I can write out that entire parentheses, because the 1/2 is attached to the parentheses. Over 2 means square root, so square root of 5x. Anything to the first power is useless because it does absolutely nothing. So to the 1/2 power just means square root. My 1 still lives on top. So technically I'm done. And I know some of you are looking at this and saying, oh, but there's a square root on the bottom. I know there's a square root on the bottom, but you know what? I'm going to leave it like this anyway because it doesn't tell us to simplify. It just tells us to write it out in radical form, which technically I did. Whether it's simplified or not, it's not my problem. Not my problem, dog. Write the expression in exponential form, all right? We've got the 4th root of 2 in a parentheses to the 5th power. There's a little rule that says b to the m over n can be written as the nth root of b and take all of it to the m power. So comparing u to u, right, I would be able to be like, oh, okay, well, you would be my n, and you would be my m, and you would be my b. So I can rewrite this out as my b, which is 2, to the m, which is 5, over the n, which is 4. And that's it. Write the expression in exponential form. There's a little rule that says b to the m over n power can be written as the nth root of that b all taken to the 5th power. So taking a look at what I have and labeling things up, I could say that you are my n, you are my m, and you are my b. So you are 2 to the 5/4 power. That's it. Write the expression in exponential form. There's a little rule that says b to the m over n can be written as the nth root of b all taken to the m power. So labeling things up, I can say that you are my n, you are my m, and this whole thing is my b. Now notice how I wrap that in parentheses. I want to keep it that way. So my b is parentheses 6x because the whole 6 and the x is going to be applied to the cube root and to the 4th power. I can't just do the x part. I can't just not have parentheses. So m was 4, n is 3. That's my answer. Simplify, parentheses, 27, p to the 6 to the 5/3 power. Whenever you take stuff that's being multiplied inside a square root and you're taking all of it to a power, you apply that power through multiplication through each exponent. So 5/3 is going to get multiplied to 6, and 5/3 is going to get multiplied to invisible 1 over here. So let's do one thing at a time. 1 times 5/3 is 27 5/3. If you watch all of my videos, and I pray that you do, you know that you can rewrite 5/3 as the cube root of whatever, in this case 27, all to the 5th power. And you know that the cube root of 27 is 3. I mean, you should know. And 3 to the 5th power is 243. So you became 243. Now let's focus on the other guy. P to the 6 to the 5/3 power means you multiply 6 to 5/3. So P is going to be 30 over 3, which all simplifies out to P to the 10th power. That's how it's done. 9r to the 4th, all in parentheses, to the 0.5 power. Fun fact, anything to the 0.5 power is the same thing as anything to the 1/2 power, and anything to the 1/2 power just means square root. So this just means the square root of 9r to the 4th. And if you break this down into simpler terms, 9 is 3 times 3, and r is r times r times r times r. All those r's. We're pirates. Get it? It's okay if you don't. Circle every identical pair of numbers or letters. So circle a pair of 3's, bring one of them out. Circle a pair of r's, bring one of them out. Circle another pair of r's, bring one of them out. So we have 3r squared and nothing left over. So that's going to be my guy. Simplify. Your answer should contain only positive exponents with no fractional exponents in the denominator. All right, well, we have 2m squared, 4m to the 3/2, 4m to the -2. They're all being multiplied. So let's make life easy and do 2 times 4 times 4, which is 2 times 4, which is 8 times 4, which is 32. And let's just move that over here. Now let's kind of write these out separately next to each other. We have m squared, m to the 3/2, and m to the -2. M squared times m to the 3/2 times m to the -2. Now what you're supposed to do is when you multiply terms of the same base, you add the exponents. Add the exponents. Now this is what I noticed right away. Well, 2 plus -2 is 0. So these guys just cancel out. Isn't that nice? So you drop down the m to the 3/2. You have the 32 living in front of it. And I'm supposed to, your answer should contain only positive exponents with no fractional exponents in the denominator. Well, I don't see any fractional exponents in the denominator, so I'm going to be done, bro. Thanks for watching, gang. Simplify. Your answer should contain only positive exponents with no fractional exponents in the denominator. Let's do this. Let's move all the 3's together. Let's move all the x's together. Let's move all the y's together. So 3, 3, 3 times 3. X to the -1/2, x to the +1/2. That's good news. So x to the -1/2. You'll see why in a second. X to the +1/2. And then y to the -1/3. It's alone. Why did I keep that red? Why did I keep it red? Let's make it a different one. Let's make it blue. Y to the -1/3. All right. And that's going to be over 3 y to the, I'm trying to find the color, sorry, y to the -7/4. All right, right away, we can do this. So that leaves us with just 3 up here. When you multiply terms of the same base, you add the exponents. So x to the -1/2, x to the +1/2, -1/2 plus +1/2 go away. They cancel each other out, become 0. So all the x's are gone. Ooh, I wish that was the story of my life, huh? And then you get y to the, well, let's do this. Let's do this. Since I'm not allowed to have negative exponents or fractions in the denominator, let's move u up, right? So we'll keep that y to the negative 1/3 there. Let's move u up by making the exponent positive. So y to the 7/4. So what that means is I have to go over here, because now I need to add these two. So negative 1/3 plus 7/4. Now I have to add fractions like I'm in freaking middle school over here. 3/3, 4/4, negative 4/12 plus 21/12. 21 minus 4 is 17/12. So you become 3y to the 17/12. That neat? That is neat. Solve the square root of negative 8 minus 2a all equals a. All right, so in order to get rid of that square root, and that's all I have on the left side, I have to square both sides. 0 squared is 0. The square root of negative 8 minus 2a all squared is just going to cancel each other out. So you're left with negative 8 minus 2a, and it's just a two-step equation. Add 8 to both sides. Add 8 to both sides, cross u out. Negative 2a equals 8. Divide both sides by negative 2. Divide both sides by negative 2. A equals negative 4. Now we go up here, we make sure it works. Negative 2 times negative 4 is positive 8, so negative 8 plus 8 is 0, and the square root of 0 is 0. Everything checks out. Solve the square root of 2m minus 6 equals the square root of 3m minus 14. Well, I have a square root on the left and a square root on the right. Let's just square both sides and get rid of them. So the square root squared is just going to become 2m minus 6. And the square root squared is just going to become 3m minus 14. And now it's an Algebra 1 problem. Let's subtract 3m from both sides. Subtract 3m from both sides. That gets me negative m minus 6 equals negative 14. Let's add 6. Let's add 6. And that's going to be negative m equals positive 8. Nope, negative 8. And if negative m is negative 8, then positive m is positive 8. Now let's go over here and make sure that that makes sense. 2 times 8 is 16. 16 minus 6 is 10, so you got the square root of 10. Right? 3 times 8 is 24. 24 minus 14 is 10, so you got the square root of 10. No negatives to be nervous about. Everything checks out. Everybody wins. Solve the square root of negative 10 plus 7p equals p. Well, in order to get rid of this square root, let's square both sides like so. The square and the square root cancel each other out, so negative 10 plus 7p equals p squared. Now what I'm going to do is I'm going to move everything to the right because this looks like a quadratic problem. So I'm going to add 10. I'm going to add 10. I'm going to subtract 7p. I'm going to subtract 7p. Cross u out. 0 equals p squared minus 7p plus 10. Now you look at this and say, yeah, that is a quadratic. Are there two numbers that add up to negative 7 and multiply out to positive 10? Yup. Two negatives, negative 5, negative 2. So, zero product property, if p minus 5 equals 0, 5 is an option. If p minus 2 equals 0, 2 is an option. So let's go over here and make sure nothing wacky happens, right? If I were to plug in 5, I would get negative 10 plus 7 times 5, right? Which is asking me to find the square root of, what's 7 times 35, the square root of 25, right? And see if that equals 5. It does. If I were to plug in the 2, that would be negative 10 plus 7 times 2, so that would be the square root of negative 10 plus 14. And I want to see if that equals 2. Negative 10 plus 14 is 4, so the square root of 4 equals 2. Checkarooski. Both of these work. Solve 27 equals x to the 3 halves. Well, in order to get rid of that 3 halves, I want to make it a 1 so x is all by itself. So why don't I multiply both sides, or not multiply, but take the 2/3 power to both sides. Take the 2/3 power. Why? Well, 3 over 2 times 2 over 3 is invisible 1. So x is now all alone. 27 to the 2/3 power can be written as the cube root of 27, all of it squared. The cube root of 27 is 3, and 3 squared is 9. So 9 is x is 9, 9 is x, and x is 9. Solve 26 equals -1 plus 27 x to the 3/4 power. Let's add 1 to both sides. So you get 27 equals 27 x in parentheses to the 3/4 power. Now that 27 and that 27, oh so tempting, but that's not what we're going to do. What we need to do is we need to get rid of that 3/4, right? So let's take the 4/3 of both sides, multiply both sides, or make the exponent of both sides to the 4/3. What that does is cancel u out, and you're left with 27x. Okay? Now 27 to the 4/3 power can be written out as the cubed root of 27, all of which to the 4th power. The cube root of 27 is 3, and 3 to the 4th power is 81. So if that equals 27x, and my job is to get x all by itself, right? Divide both sides by 27, divide both sides by 27, and 81 over 27 is tree. And that's it. Graph y equals the square root of x plus 5. The square root of x all alone, right, is going to look something like this. Okay? Now the square root of x plus 5 is a translation up 5. So what I'm going to do is I know that this is going to start at 0 and work its way up 1, 2, 3. I'm not going to plug in -1 because I can't. So I'm going to make a little table. Okay, I'm going to make a little table of x and y values. I'm going to do 0, 1. I don't want to do the square root of 2, so I'll do the square root of 4. And I don't want to do the square root of, I can't even make it out to the square root of 9, so I'm just going to use these guys. Okay, now why didn't I do the square root of 2? I don't know what it is. So if I just use 0, 1, and 4, I'm good. The square root of 0 is 0, and 0 plus 5 is 5. The square root of 1 is 1, and 1 plus 5 is 6. The square root of 4 is 2, and 2 plus 5 is 7. Okay, so I have 0, 5, 1, 6, and 4, 7. And so this shape, this curve-looking shape, is going to take place like that. And that's the graph of a square root. Graph the square root of x minus 4 minus 2. Well, fun fact is if you have a -4 living inside a square root, and let's just make something very clear. Square roots look like this. So having a -4 inside the square root tells you you move that to the right 4 spaces. Having a -2 outside the square root tells you that you go down 2 spaces. So my picture is going to look something similar to that. Okay, so what can I plug in? Well, if I start at 4, I can't plug anything less than 4 because none of it exists. So what I can do is I can pick values that I know I can take the square root of. Right? If I plug in 4, I get 4 minus 4 is 0. I can take the square root of that. If I plug in 5, I get 5 minus 1, or 5 minus 4, which is 1. The square root of 1 is 1. I can do that. Now the next perfect square is 4. So the next number I'm going to use is 8. So if I do 4, I get the square root of 4 minus 2, which is 0, and 0 minus 2 is -2. If I do 5, I get the square root of 5 minus 4, which is 1. And the square root of 1 is 1. 1 minus 2 is -1. And if I do 8, that's the square root of 4 minus 2. 2 minus 2 is 0. So my picture is going to look like 4, -2, 5, -1, and 8, 0. Just try to draw like a nice looking curve like that. It's not the prettiest. It's not the prettiest, but it's supposed to look something like that, and they kind of ended up looking like that. And that'll do it. That'll do it for radicals, baby.